Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to this next lecture in this particular course of Analytical, Spectral and Microscopy applications of inorganic compounds and nanomaterials. Just in the previous class I have been talking, I initiated the process explaining the emission, in particular fluorescence and phosphorescence, and I have also explained all the basic concepts associated with it, particularly those processes which compete with that of the fluorescence emission process. Now in this class, maybe in the one or two more classes to come up, we will look at all application aspects of this and try to understand both some simple organic systems and a lot of inorganic systems. Also we will look at some nano material ones, analytical applications, all of these kind of things we will look at as we keep moving across these lectures. Now, so kindly have a look at this particular slide. We have some heterocycles like the pyridine, furon, thiophene, pyrrole. I am just showing on the slide, and now you have a few of these here, and this pyridine is fused with another benzene ring, the isoquinoline kind of thing in this pyrrole is fused with that. Similarly, you can fuse the thiophene, all of this, furon, everything you can fuse with that. So what is that what we are looking at? If you look at these ones, there is not much of a fluorescence emission. Why? Because there are lone pair of electrons which disturb this pi to pi star and then make more of a n to pi star kind of things. So the fluorescence is not completely quenched, but fluorescence intensity is lower in that. But on the other hand, if you put this pi system coupled with that, please have a look at it, and this pi system is coupled with that, and that effect of this, the lone pair, is extended into the pi system. So therefore still the pi to pi star transitions, and that means reverse pi star to pi are still feasible, and then you have a stronger fluorescence coming up as compared to the simple this pyridine, furon, etc. Okay, come on to this example on the right top here. First look at this particular thing. So phenyl and phenyl connected by this bond. This bond is a single bond. So which means we can understand that there is a huge amount of rotation about this single bond is possible. So you have a phenyl moiety, and so you have another phenyl moiety. Okay, so you have a rotation on this. So if you look at the fluorescence spectrum, this gives very little fluorescence, almost no fluorescence kind of thing. The reason is during the excited state, this rotation is much faster than the emission process. So therefore it goes through it loses its excited state energy through the rotational process, hence you do not find the fluorescence, or you find very little other fluorescence. Now you tie these two together, you tie this one, finished. So you just now made a resid. So this thing is now stopped. So there is no internal rotation at all. Hardly any kind of a rotation you can expect, because the entire thing is fused. Now what is that? This fluorescence you measure is very high. So this is again, it tells you the rigidity as well as the two planar things are put together in this. So the planarity, rigidity, all of these. So you have removed this freedom to rotation and made a constraint. Okay, you can also look at another example just below that in the same slide, and you have this hydroxyquinoline. So this hydroxyquinoline part of that. So you have in this So this is the hydroxyquinoline, and when you make the zinc complex, this proton will go and this will be the, because this minus charge will bind with that. So prior to that you have this one. So there are two systems, one is the hydroxyquinoline and the hydroxyquinoline which is bonded to the zinc. So hydroxyquinoline, you have a little fluorescence, the fluorescence will be there but it will be much less, and when you put with the zinc, so when you put with the zinc, so you have, so this goes out and then one more molecule, so it will form zinc with L, if you call this as L, so that will be twice, so that makes a complex. So that complex it shows the very good fluorescence, not because of the zinc it's showing, it is because of this molecule itself which is got stabilized by this in the form of a chelation. So generally in the literature they call this as the chelation assisted fluorescence enhancement. Okay, so that's also fine. Now you look at this example on the slide, the aniline, various resonance forms of the aniline, anilinium ion. So again the fluorescence of each of these is obviously will vary, and the species is dependent on the pH and the medium, etc. So therefore the species, which one of these is it a more neutral form is more percentage, or is it the ionic form is more percentage, that will depend on your solvent. So therefore your emission will also depend on the solvent and its pH, etc. that. So let us look at a little aspect of the fluorescence, no fluorescence, less fluorescence kind of thing. Okay, so how this is explained? So your pi to pi star is your absorption, and pi star to pi is your emission. So now we need to look at how this pi star to pi is more favored, that means your fluorescence efficiency is increased. If that is less favored, that means fluorescence efficiency is decreased. So that is how it is. For example, you take here the benzene as the in this case as a standard, and the fluorescence emission here is, let's say, something like 10 relative units, and you take the toluene as 17, the propyl isopropyl benzene or propyl benzene is 17. So you have an enhancement of this with the alkyl group being present there, which means is favoring more of the phi to pi star transition in absorption. Therefore the return is the pi star to pi gets more intensity in that. Now you take with replace one of the hydrogen by fluorine, not much difference will be there, but if you change by chlorine, the fluorescence start decreasing. Please look at this table which I am showing on the slide, and if you replace the hydrogen by bromine, then it is half of its intensity. Make it by iodine, it's much more. Okay, the fluorine, chlorine, bromine, iodine. So one thing is that they all have the 3 unpaired lone pair of electrons are there, and the size is increasing as you go from fluorine, the very small in size, to the chlorine, the bigger in size, to the bromine, to the iodine, the size is also increasing. So both the effect of that electrons as well as the effect of the size, and that is what is referred as the heavy atom effect, which we will not go into the details of that, but the heavy atoms will also quench. So therefore your fluorescence is gradually decreasing from 10 to 7 means 30% decrease, 10 to 5 means 50% decrease, 10 to 0 means 100% quench. So that is the kind of things you have. So now you take phenol going from 10 to 18, almost double the intensity, then the phenoxide goes back to almost like a benzene kind of thing, and the methoxy benzene is again high. So that means if you have some kind of a electron releasing kind of a groups of that, will also make transitions more effective for the pi to pi star. Therefore the reverse is also more effective. Now you look at something like aniline, the NH2 group, benzene with the H group, so it's roughly double. Now you protonate this aniline, the anilinium ion, everything gets quenched. So you have seen that here, this is the anilinium cation. So the fluorescence is completely quenched. That means in acidic solutions, your aniline group may not be in the aniline stage, it will be anilinium ion. So you can easily make out what percentage of this your molecules got protonated. So you can do quantification also based on this as well. So similarly, benzoic acid as compared to the benzene, it's reduced by 70%, benzene 10, benzoic acid is 3, that means 70% quenching has happened. Now you put cyanobenzene or benzene nitrile, it becomes the double, 10 becomes 20, and you put the nitrobenzene, becomes 0 again. So electron releasing, electron withdrawing, heavy atom, if you have a large number of pi electrons or unpaired electrons, coupling with the pi system, all of these will change your emission process. That's what you can understand. So the take home message from this particular table is that the transitions of pi to pi star in the absorption spectrum, if you are greater strong, then you can expect the better the fluorescence emission, otherwise the fluorescence will get reduced or quenched. And these are affected by the electron releasing, electron withdrawing, protonation, deprotonation, all these kinds of things. And on the substituent, any heavy atom as a substituent electron, the unpaired, the lone pair electrons, they will also get affecting your pi system. So the pi system, anything that affects the pi system, so the pi to pi star will get affected, therefore your absorption will get affected and your emission will also get affected. So these are the kinds of things. Now look at some examples into the coordination chemistry aspects of it. Now look at one molecule, is a non-cyclic, so and is a ligand you can call, because there is a ligating center, there is a phenolic center, imine and phenol. So this is what, if I draw a line here, it is like a symmetric. If I draw another line here, there is a symmetric. So you have 1, 2, 3, 4 tetradentation on this side, 1, 2, 3, again this 4 tetradentation from this side, where this being common. So this is you can see roughly when a metal ion comes, a metal ion can come into this kind of a region, can come into this region, maybe both of these sites can also be filled. So now the coordination chemistry aspect. So please look at the slide. I am explaining that you have these 4 and you have again these 4, the metal ion can come here, the metal ion can come here, so you can have a coordination complex in these things. So here we talked about the 2 metal ion titrations, of which one is with the zinc, other is with the cobalt. First let us look at the zinc kind of a thing, and this first spectrum is from the ligand. There is a fluorescence emission which is around this 460, 462 or somewhere here, and this fluorescence emission increases in intensity by little more etc. as you keep adding more and more zinc. So now this plot shows you the amount of zinc 2+ added versus the on the y-axis is the fluorescence intensity. Now you see that this is nothing but a fluorescence titration. I showed you similar things for absorption titration in the previous topic, and I showed you how one can derive the ratio between the metal ion and the ligand, or ligand and metal ion, when it forms a complex. Same kind of principle is extended here, except that here the measurement is emission or fluorescence, there the measurement is absorption. So your y-axis is nothing but the amount of the mole ratio of the metal ion added per given mole of the ligand. So that means the concentration of the metal ion by the concentration of the ligand, that will give you the, you can get them in the mole ratio. So you can see in this particular case, you can see that the intensity is increasing almost linearly and saturates somewhere around here. If you draw this line, this is what, 2. So that means that the zinc to the ligand is 2 is 1. So that means one ligand is able to bind to 2 zinc species. So you can see this one zinc species here can go, other zinc species can come here, and it is density is increasing. We will see why it's increasing etc. what is making. Now on the other hand, if you do the same titration, this is the ligand, and for the cobalt as you add, it will start decreasing, almost quenching. So it's going from the value of somewhere 400 to around 400 or so. So here this has gone from somewhere 400 to 1800, increased by 4-fold or more. Here it is decreased. So this is called quenching. So when you add the cobalt ions, so you have a quenching of the fluorescence is happening. and I have not shown all the spectra, but it just, you can take it as granted that is where the thing is. So this is your ligand fluorescence spectrum, and this is your zinc complex fluorescence spectrum, and the red one is for your cobalt. Why in case of zinc you have an enhancement, why in case of cobalt you have a decrease in this? So we have seen earlier, any process that could be geometry or anything, rigidity, which influence the pi to pi star, here this is basically because of the pi to pi star interligand. So you have the pi to pi star which is influenced by this extended this, so whole thing is extended. So if any portion gets little less planar, then you will have a less pi to pi star strength, etc. So that rigidity, planarity are all important. So why is that the zinc has got the enhancement, why the cobalt has got the quenching? So let us address that by looking into this. So we looked into this particular paper which published the crystal structures of this. If you look at the crystal structures of the cobalt and the zinc, then in the lattice, the asymmetric unit cell of the lattice, there are two dimers are there. So this is one dimer of the cobalt, another dimer cobalt, and these are the ligands. Okay. So one ligand, two metal ions cobalt, another ligand cobalt. But if you look at very fine focus at the center of the cobalt here, this is like the TB, trigonal bipyramidal. And if you look at this particular part of the cobalt, and that is like a square pyramidal. And if you look at this particular one here, again another cobalt here, other cobalt here. So you have a different kind of a structural motifs are formed. And similarly, if you look at the crystal structure, the zinc 2 complex, again it has the two independent molecules, chemically different, structurally different in both the cases. Now if you look at the zinc is here, another zinc it is here, this zinc is here, this zinc is here. So you have different kinds of things are there. Now if you put this compound into the solution, obviously the solvent can also play a role in the coordination numbers. So in effect what is happening was, in case of zinc, whatever the ligand pi structure gets more planarized, so the planar kind of a thing, rigid, as compared to that of the cobalt. So that's why in the cobalt you see that it is a quenching, and you see it is enhancing in case of the zinc. So these are all in solid state, but in solution you have to be careful that the solvent ion can also influence by binding, they change the coordination geometries as well. So we are not looking at the rigidity of this, but we are looking at the rigidity of the ligand, because what you are looking at in the fluorescence spectrum is the pi star to pi of the ligand, not from the metal. So that is where that one needs to keep that in mind. So the favor. So in effect, in case of the zinc complexes, this pi to pi star is more favored, so the pi star to pi for the transition is more intense, and this becomes quenched in case of the cobalt complex. I hope that is clear to you, the why the cobalt is intensity is decreasing, the zinc is increasing. We don't have the exactly coordination spheres in the solvent, but we can make, you can guess, because the solvent can also involve in the binding process of that. So overall you can think the more favorability for zinc in terms of the tetrahedral structures, and more favorability for cobalt is octahedral structures. So in order to form that, the molecule takes some different kinds of the geometric favorabilities, and that will change the pi to pi star effect of that. Okay, let us look at one other case of this the complex, the nickel and copper. So let us look at the nickel trinuclear complex. Please have a look at the slide is here, and this is a terminal nickel, another terminal nickel having a solvent. Now the central one is bounded by this, all these 6. Now if this solvent is methanol, that's referred as 1, compound 1. If the solvent is propanol, is labeled as 2. If the solvent is DMF, 3. So you have just the change of the solvent, 3 complexes. Now you look at this, the ligand is the fluorescence spectrum is here, and which is giving the emission around 507, and when this is excited at 324. Now these complexes of the nickel are excited at 378 nanometer and the emission is measured. You see that this one is a green is a compound 1, compound 1 is with methanol, and this bluish one is 2 with the propanol, and the purple one is 3 with the DMF. So you have a difference in their positions, not a lot, but there is a little. The 519, 523, 522, 521, the different. In spite, the excitation is same for all of them at these ones or that. So all these 1 to 4 are excited at 378 and the ligand is excited at the 324. So with respect to the ligand, these are all quenched to some extent. Among these complexes, there is a shift. This shift is because of the charge transfer transition between the solvent and the metal ion. In one case DMF, other case propanol, other case methanol. That makes the ligand to metal charge transfer variation. So whenever you have a charge transfer happening from ligand or metal, ligand to metal or metal to ligand, there will be a difference in your fluorescence. Either fluorescence may get enhanced or the fluorescence may get quenched also. So that is where what you look at. Now if you take with the same similar kind of the ligand, but not this complete ligand, is a part of that, and make a copper complex of this. So this copper complex, when you excite at 378, it gives much lower of this. But this ligand is a little different from this one. This is a connected ligand. Here what you have is up to here. You cut this one and make. So this, the 1:2 ratio of this, and then this has got a somewhat lower kind of thing. So you can see the ligand to metal charge transfer is somewhat different in this case, somewhat different in these cases. So therefore you have further, not a lot different, but there is some considerable difference in the peak emission position, but emission intensity gets affected. So these are the parameters which are very important when you are looking at the fluorescence emission spectrum. I hope you got the idea how your pi to pi star transition is getting affected during the complexation, during the geometry, octahedral, tetrahedral, other kinds of things. Okay, let us look at another example here. It's a manganese complex of this kind of a carboxylate system, and it forms a tetranuclear manganese 2 complex here. So you can see the structure that in this on this slide on the right and the top, the manganese 1, 2, 3, 4, and the 2 terminal manganese 2 internal. Okay, and this is connected with actually a different, this ligand is a core ligand is this one, and then you extend this with the carboxylate, extend with the carboxylate, and carboxylate. Now you change this to the manganese centers. Manganese is bonded here, bonded here, bonded here, bonded here. Now this particular compound has a kind of a crevice or cavity here, kind of a crevice or cavity here. So you can see that, and these are useful. So you can use for some molecules can come and interact with it. Now let us look at 2 experiments. One experiment is this one. This particular compound is studied at different wavelength in different solvents, the emission. So the solvents are hexane, toluene, benzene, chloroform, ethanol, methanol, all these things. You can see from here that's going over there. Okay, so your there is a huge amount of emission wavelength shift. So going from somewhere around 400, close to that around 450. So if you look at in terms of the wave numbers, it will go to 22,500 to 24,500, which is around 2,000 centimeter inverse variation. Now if I take the polarity of each of these solvent and put on the x-axis, and if I take the emission wavelength in terms of the nu bar, okay, I get, and I can make a kind of a straight line between these 2 systems. You can see that very well. So very well correlated to the polarity. So why the lambda is shifting? In spite the compound is same, you are putting in different solvents. That's all you are doing. So in one case hexane, other case benzene, toluene, chloroform, dichloromethane kind of things, etc., etc. DMF, acetonitrile, ethanol, methanol, etc. Changing. Compound is not different. Compound is the same. So your emission process. So the emission is also influenced polarity of the medium. Polarity versus the non-polarity of that will make. So it is moving to the higher wavelength, means what? The energy gap is getting decreased. So that means your pi to pi star energy gap, there is, in other words, pi star to pi, one and the same, that energy gap is being changed. Okay. So therefore you have your fluorescence emission occurring at a different. So this is very nice. So one can use by tuning the solvent polarity, you can tune the fluorescence properties, fluorescence emission property of that. So what is the second demonstration done in this particular example? If you take this particular compound, as I said, there is a crevice here where you can have some molecules interacting here. So in this case, the nitro aromatic guest species have been reacted with it, and many of them do not show much difference, but trinitrotoluene shows a fluorescence quenching. So if you have a small amount of TNT, less quenching. As you increase the concentration of TNT, it will be increasing. So please look at this particular slide. The fluorescence emission of this particular compound is here, TNT added. As you add TNT, it drop down, drops down, etc., etc. So if you take this intensity and normalize with the intensity of the starting, then you can get and plot that on the y-axis and the concentration of the TNT. So you can make very nice linear kind of a plot you are getting. So intensity ratio versus this concentration. That means you can use to quantify the amount of TNT present. That means it acts like a sensor. So this will be, this compound can act like a the trinitrotoluene sensor by using the fluorescence method. Of course, if you look at this lattice, you have a very huge the 3D network formed in that. You can see the channels and then regions where these. So that is not a part necessary for this particular course. All that this is, you can use quantitatively the decrease in the kind of thing. Okay, let us look at another example, this coordination chemistry aspects of it by looking at even the ligand. So you have a molecule of this. Kindly look at the slide, please. So you have a group like this you can call it as a acceptor kind of a group with this cyclic ester, and the amino group, which you can call it as a donor. So you have both the donor, electron donor and acceptor in the same molecule you have. Okay. So if you look at this particular molecule with R is equal to H, it shows a fluorescence emission here, quite good. Now if I change this to the chlorine here, okay, and this intensity gets further enhanced. And on the other hand, if I put NO2 group here, it's completely quenched. Why should that happen? That means this particular group is involved in affecting this electron transfer process. So you have with H, you have this one fluorescence. Now if you put for chlorine, when you put the NO2, it gets quenched. Let us say it's quenched because of the electron withdrawing effect of this, electron withdrawing effect of this one. So therefore that will allow a greater participation of this electron transfer from here to there. So therefore it quenches. If I have the chlorine you can take in both the ways. One is as an electron withdrawing kind of thing, but that is not very important. What is important is you have 3 lone pairs are there. The 3 lone pairs can couple with this pi system and contribute to the pi to pi star rather than contribute towards this one. So it will not accept as an electrons, but it will affect the pi system itself, and therefore your fluorescence intensity is enhanced dramatically, means by 2 or 2.5 fold. So therefore these things are very important with respect to, so electron donor property, electron acceptor property, and the influence of that. So there is influence of this by this particular group. The one time hydrogen, other time chlorine, other time nitro group makes. Another aspect also explained in the same slide here is that you take this compound and add some iron 3 plus. So when you use the iron 3 plus, as you keep adding more and more iron 3 plus, the fluorescence intensity get quenched. So little further quench, etc. So this quench, because it forms complex of these, though it utilizes the pi electrons of the unpaired, the non-bonded electrons of these heteroatoms, still it quenches because of these groups, because it's not just this one. You will have more number of molecules associated with the coordination complex of the iron, because the iron tries to prefer the 6 coordination in this. So therefore the overall geometry of these ones, because the flexibility of these is also important. So the rotation about this one, the rotation about these ones will also be important, besides taking the electrons to bind. So you are taking electrons to bind from here to the iron center. That is fine, but still you are increasing this kind of a flexibilities during the in the excited state. Therefore the quenching takes place. So therefore the quench, and of course this, as a result of that, this acts like a fluorescence quencher sensor. So in presence of iron ions, again, detection limit is almost 2 micromolar, and the environmental agency talks about 5 micromolar. Below anything is a good one, and this is a good kind of a sensor for that. Okay, so I think so we are looking at a lot of examples of this. Anyhow, we need to continue that further. So in the next class I will give some more examples of this. Then we will look at some the nanomaterial kind of thing, how it happens. Fret process I have not explained, that also will take care of in that, and any analytical kind of applications, all this. Maybe it might probably take next at least a couple of more classes. So keep going through these things, and then make yourself familiarized with the first lecture so that you will understand the applications much better. Thank you very much.